Welcome back. So we're going to continue with this topic of continuity. And as you can tell from the previous few videos, what we've been doing is building a library of sorts of examples of continuous operations, continuous functions defined over all sorts of metric spaces. We're going to continue doing that by considering two specific classes of functions between vector spaces. So throughout this video, I'm going to be talking specifically about things defined over metric spaces. So let's say that I have I'm going to talk about vector spaces, right? And later we're going to assume that they have norms. Okay, by definition, a transformation, a function from V to W is linear if for all V prime elements of V, for all lambda in R, if I look at this linear combination lambda V plus V prime, and then I apply T, right? If I compute the linear combination and then apply T, that's the same as first computing T of the individual terms and then doing the linear combination. So that's what a linear transformation is. We're going to see that multilinear is something related to this, but for now, I'm going to stick with this one. Now, let's assume that that both V and W, have norms, right? So we know what norms are by now, hopefully. In that case, I can define what I'm going to call the norm of linear transformation T, which is a sup over V in the space V non-zero, of the norm of T V divided by the norm of V. Okay, so the supremum is telling me by how much the norm of T of V can be larger than the norm of V. Like, this is just like the operator norm defined for matrices. And there's not a coincidence, right? So because a matrix is defined linear transformations between Rd and Rk, right? K plus a times D matrix defines a linear transformation between Rd and Rk. And the operator norm that we defined is precisely a specific example of this norm when V is Rd with the Euclidean norm and W is Rk with the Euclidean norm as well. Right, so we have this object. A priori, it's a supremum, but we don't know that it's finite, right? So this could be infinite, and we're going to see at least one example that's natural, important for analysis, where this norm, we're calling it a norm, though we haven't proven that it's a norm. Bear with me. In any case, we're going to be considering examples where this is finite, examples where this is infinite, and we're going to say a linear transformation is bounded precisely when the supremum is finite. And of course, we know many examples of these things. We know, for instance, that we know linear functionals, right, from a vector space to R. The specific case where W is equal to R, right? R is a vector space over itself. We know that matrices, as I said, give us linear transformations between Rd and Rk, right? So K times Z matrices give us linear transformation between Rd and Rk. We've also seen that if the operation of taking a function, right, in that space C that we've been talking about, that operation of taking a function and integrating it is linear. So that's another example of linear operation. And we're going to see that all these examples give us bounded operators, which is very important from the perspective of continuity because of the following theorem. The theorem says that if I have a linear transformation and then T is continuous, well, according to norms V W, right? I have to specify the norms, or have to specify a way of measuring distances, and I know the norms gives us a way of defining metrics. So suppose I have this norm in V, have this norm in W. T is going to be continuous with respect to those norms if and only if T is bounded, which, as I said, means that this T V arrow W, the supremum, is finite. This is the definition of what it means for something to be bounded. Okay, so we're going to prove this theorem and then use it as a criterion to prove, for instance, that all linear transformations between Rd and Rk are continuous because they're bounded. We've sort of proven that already by showing that this operator norm on matrices is well defined, with the meaning it's a finite number, it's a finite real number. Then we're going to consider examples where there's space of continuous functions, there's space of differentiable functions, and in that case, we're going to see some things that are bounded, some things that are not bounded. Okay, but let's first prove this theorem, and I'm going to start with the easy direction. The easy direction says that when something is bounded, it's continuous. So it goes this way, right? Okay. So my claim is that in this case, if this norm here, what I'm calling a norm of T, right? If this thing is finite, T is Lipschitz, and its Lipschitz constant is precisely this thing here. Right, so we know from previous lecture that Lipschitz functions are continuous, so proving that T is Lipschitz it's sufficient to show that it's continuous. Okay, how do we do this? Okay, what do we need to prove to show that something is Lipschitz, right? So we want to prove something like this. That norm of TV minus TV prime is less than, well, the Lipschitz constant, which is this guy, right? So right now this is still conjectural. We haven't shown this. Right? And how do we do that? It's actually pretty simple, okay? But we have to use this linearity property, right? Notice that here I have T of one vector minus T of another vector. Well, I mean, we can be very detail-oriented here, but I'd just say, okay, so it's a linear combination of T's. And as I said, the linear combination of T's is the same thing as T of the linear combination, meaning this is exactly equal to T of V minus V prime. If you want, you can look, well, this is V plus the vector V prime multiplied by minus 1, so it is an expression of that form. Maybe you have to flip the rows of V and V prime, but that's no big deal. Okay, good. So we have this. So look at what's happening now. We're comparing T applied to a vector to the vector itself, right? So when V is different from V prime, we know that this thing here what is this? So it's T of a vector divided by the norm of the vector. We know that that thing for all non-zero vectors is at most the norm of the transformation T. Right? That's what this thing means. Okay, I know this is a soup, and here I'm looking at one specific vector, so it should be bounded by the soup. The soup is a non-prime. And now we're done, right? Because this gives us, right? We wanted to prove this thing. And we observed, okay, this is T of the difference, and we have this ratio. Therefore, T, this side, is bounded by this side. Well, I proved it when V is different from V prime, but you must agree with me that when V is equal to V prime, then everything here is 0, right? So there's nothing to be proven. Okay, so that's good because basically by using linearity, we reduce this bound to something about this ratio, which is bounded naturally by the operator norm, or the norm of the linear transformation. Well, the other direction is a little bit harder, but not by much. And we've seen a very similar proof when I showed you that I gave you this necessary and sufficient condition for two norms to be equivalent. So norms of the same metric space will be equivalent. So let me reverse the arrow. Okay, so what we're going to do now is to show that when t is continuous, it's bounded. Here's something that we need to use, right? So a fact that's true of all linear transformations, regardless of whether they're bounded or not. The zero vector is always mapped to the zero vector. Well, how do we prove that? Well, there are many ways. You can take, say, lambda equals 1, v equal to v prime equal to 0 here. So you get that t of 0 minus 0, which is t of 0, is equal to t of 0 plus t of 0. So t of 0 is equal to twice t of 0. And that means that t of 0 must be 0 as well. Right? So you have to play a little bit with the axioms of vector space to get this, but it's easy. And we're going to assume it as a fact. Okay, good. So if t is continuous, and we have a sequence in the space V converging to 0, we must have that t of V sub n converges to 0 of W, right? Continuity means that if V sub n converges to something, t of V sub n converges to t of that something. And that's what we have here. Okay, so continuity means, well, basically we're saying, if t is continuous, it must be continuous at 0, and therefore t of Vn converges to 0 of W whenever Vn converges to 0 of V. Good, because now we're going to prove that when t is continuous, it has to be bounded, and we're going to do that by contradiction. And what we're going to do exactly, we are going to show that if t is continuous and it's not bounded, then we are in trouble. Assume t continuous, but not bounded. And what does it mean to say that it's not bounded? It means that the supremum is infinite, and therefore, for all c, there exists a vector v sub c in V that's non-zero, such that the ratio over there is greater than or equal to c. This is when it starts looking similar to this proof related to equivalence of norms. That time we did something that I'm going to do again now. I'm just going to say, well, if this holds for all c, I want to get a sequence somehow because I want to relate this to continuity. So I'm just going to say for all natural numbers, I have a v sub n such that t v sub n by v sub n is greater than or equal to n. So if we look at what's going on here, this is saying I have vectors whose, when I apply t to them, the ratio between t v sub n and v sub n gets larger and larger. From these, I'm going to build vectors that go to 0, such that this ratio still gets larger and larger. And that's going to be our contradiction. Okay, so what are these vectors? I'm going to define x sub n as v sub n divided by the norm of v sub n. And I have to divide by something here that goes to 0 but doesn't go to goes to infinity, but doesn't go to infinity too fast. So let me say square root of n. Right, so this is another sequence. And I can look at what happens to those guys, right? First of all, what's the norm of x sub n? Well, if we really want to be careful, we have to apply all properties of a norm. This is v sub n multiplied by scalar, or divided by scalar. So the scalar comes outside of the norm. So this is 1 over square root of n. And in particular, we see because 1 over square root of n goes to 0, the sequence x sub n, right? These are vectors in V, and these vectors are going to 0 V. Right? It's just saying the distance between x sub n and 0, which is just a norm of x sub n by definition, is going to 0. Now, when you compute the norm of t xn, well, again, x sub n is v sub n divided by scalar, right? So when you compute the norm, the scalar goes outside, because we know that when you take a linear transformation and there's a scalar, the scalar can be moved outside. So what do we get when we move the scalar outside? We get t of vn divided by this denominator here. And what is that? Well, that's t of v sub n w divided by square root of n, norm of v sub n. Remember that this ratio here is greater than n, so this is greater than square root of n. So here's our contradiction. The norm of x sub n is going to 0. Therefore, x sub n is converging to 0. On the other hand, the norm of t of x sub n is going to infinity. Therefore, t of x sub n is not going to 0. But remember, we noticed that if t is continuous, it must be that for any sequence that goes to 0, when you apply t to it, this thing also goes to 0. So we have our contradiction, right? So if it cannot be the case that t is both continuous and not bounded. Okay, what does the contradiction tell us? It tells us that these things are incompatible, therefore continuity implies boundedness, which is what we wanted to prove. Okay, so now we have this if and only if criterion for when a linear transformation is continuous. It's if and only if it's bounded. That's good because we're going to use this many times. And as I mentioned, the first example is very fundamental. The first case we're going to apply this to show that any, or if you want, every single linear transformation from Rd to Rk is bounded. And in order to do that, I'll end up reviewing a few things that we should know or remember from linear algebra. Okay, so I forgot this one was wet, sorry. Now I have to rub this a little bit more. Okay, whatever. Right, so suppose I have a linear transformation from Rd to Rk. So this linear transformation takes vectors x and produces vectors t of x. We're going to, these two spaces have been given their respective Euclidean norms, right? So we're going to show linear, and in this case, I've got to show that, basically I'm going to show that what I'm going to call the 2-2 norm is finite, always, regardless of what t is, as long as it's linear, then it's bounded. Therefore, it's continuous. Right, and as I said, this has to do with with the connection between matrices, right? So we know that there exists a matrix Rk times G. So it has K rows, D columns, so such that for all x in Rg, Tx is equal to, let me call this matrix A sub T. A sub Tx. And what does it mean, right? So it means the following. That for any if you look at the coordinates of this guy, so it had Txi, right? The ith coordinate of Tx is given by this sum. Right, you take, right, if you were to draw, here you have Tx, here you have A and X, right? So Tx and X are column vectors. And the entries of Tx are like the inner products of the rows of A with this column vector X. So this is basically what the formula is telling you. Okay, right, I forgot the A sub T here. Let me just mention that there's a quick and dirty formula for these entries that if you want to get the linear transformation from T, the matrix from the linear transformation, sorry, well, you need to specify a basis. So let's say the canonical basis. And this is just EI T of Ej. So that's how you get the entries of the matrix, right? So the entries are determined by T and the choice of basis. Okay, so this is our fact. And maybe I'm going to erase my little picture here because I need a little bit of space. So what do we do with this? So we want to prove that T is bounded, right? So what do I need to do, right? So I need to be able to say that the ratio of norm of T of X, where I'm using X here instead of V. So the ratio of the norm of T of X to the norm of X is always bounded. That's the same thing as saying that the norm of T of X is at most some constant times the norm of X. So let's try to just get a boundedness norm, right? So we're going to compute the norm of T of X. It's the Euclidean norm. And so in order to compute it, we have to look at the squares of these coordinates, add them up, and then take the square root. So let me first look at a single coordinate, right? So the coordinates are here. I'm going to take the square. So this is exactly equal, right? So just from the formula that I wrote over there. But now I want to get a bound on this. And remember what I told you, right? So these guys, they're inner products of the column vector X with the rows of matrix A, right? So rows, columns. So this is an inner product, and you can apply Cauchy-Schwarz to this, right? Remember that Cauchy-Schwarz tells us that the inner product is always less than the product of the Euclidean norms. So, okay, I'm applying it to the vector X, which has these coordinates, and I'm applying it to the vector corresponding to the ith row of A, which has coordinates AI1, AI2, all the way up to AID. So here's what I get. So the norm of this row of A, squared, I have to take the square root to get the norm, but I have a square outside, so I don't care. And then I have the norm of X squared. Okay, this is excellent because remember we want to compute the norm of Tx, right? So maybe I should be even more careful with my parentheses here. So I take the coordinates of Tx, I square them, and then I add them up. And let me change this a little bit so that you notice that now what's going to happen is that you're going to have a double sum here. Right, so this term is fixed. It doesn't depend on I. Whereas this other term here, I just have this sum. Right, so I have a sum here in K as well. Sorry, in I equals 1 to K. And this is bounded by this. And now look, this is the constant we're looking for, basically. Let's call M squared by definition, is the sum of the entries of matrix A. Sorry, this should be A sub t, right? The whole time. So m squared is just the sum of the entries of A all squared. So m is the square root of that. What we have shown is that the norm of Tx, Euclidean, is less than m, right, I'm taking square roots now. It's less than m times the norm of x. Which means that the ratio of Tx to x over all non-zero vectors is upper bounded by m. And it means that right, so I'm using the symbol because we have many norms for our D and RK. Here I'm specifying that I'm using the Euclidean norm. So the operator norm is bounded by m. M is a finite number, right? As I said, m is the square root of the sums of the squares of the entries of A. And that's how we prove that any linear transformation from RD to RK is bounded. Here we have the bound. I have even an explicit bound for the operator norm. Okay, that's good. So we know that our criterion is good for something. It tells us that all linear transformations from RD to RK are bounded. So we don't really have to worry about them in the sense that they're nice and amenable objects from the point of view of analysis. We can do limits. Now let's look at a few other examples which are defined over what we could call infinite dimensional spaces. I mean, that's the correct name. There's nothing wrong with it. Except they're not really talking about what it means to be infinite dimensional in this class. Some of you might have been exposed to this concept, but I mean, the important thing is that, okay, in RD, in order to specify a vector, I need to specify a finite list of real numbers, which are the coordinates of a vector. And there's this concept of dimension, right? So we know that RD has a finite basis of size D, and all bases of it have size D. D is the size of the largest linearly independent set. None of that holds in a space like C, right? So let me remind you what C is. So we've been talking about C as the space of continuous functions from the closed interval 0, 1 to R. I want to be slightly more general and suggest that the whole time we could be talking about C of a compact interval of the real line to R with the sup norm. And that's really the same thing, right? So, I mean, we've done it with the interval 0, 1, but things don't really change too much. You can check it as if you like. You can realize that that's like, it's really the same set of functions as long as you do a transformation to change their domain. Okay, but now let's talk about linear functions here. One of them we have already seen, right? Fix, so example 1, fix a t in the interval AB. We saw these linear functionals from C, this C, to R that take a function f and simply compute the value of function f at point t. So there's a linear functional. What's the difference between a linear functional and a linear transformation? Well, a linear functional is a particular case where W, right, the target space, is the real line. What's the norm of this linear functional? Well, notice that for all functions in C, etf, what is this thing? Okay, how do you measure norms on this side? It's just the absolute value. What is this thing? I'm just computing f at t. So I'm looking at f of t, absolute value. And this is less than the sup. Let me write it maybe one last time, the sup explicitly, which is, of course, just the infinity norm of f. So the ratio of et of f by the norm of f is always upper bounded by 1. And therefore, et as a linear transformation from C to R has a bounded norm bounded by 1. And in fact, it's equal to 1 because it's easy to see that if f is constantly equal to 1, then you get equality here. So if you want, we have, that's one example of a linear transformation or a linear functional for which you can exactly compute the norm. And this is one first example. Great. Okay, let's look at a second example of a linear transformation from C to itself. Okay, so example 2. It's what? So now I'm going to use this script I. It's a linear transformation from C to itself. It takes a function f and sends it to its indefinite integral. What does that mean? So it sends f to another function, if, defined so that for any t in our interval, if of t is equal to the integral from a to t of f of s ds. That's a definition. Let's see that everything works, right? So first of all, this makes sense, right? So if I wanted from an old function, let's say for an input function f, I wanted to define an output function. How do I define the output function? I have to specify its value over all points of the domain. How do I do that? By this integral. That's a definition. This defines a function. This function is differentiable because of the fundamental theorem of calculus, right? It guarantees that this integral is differentiable. In particular, since differentiable functions are continuous, it means that I of f is continuous and whenever f is continuous. And that means that we have a well-defined mapping from C to C. How do I know it's linear? Well, that's really a matter of checking definitions, right? What happens if I add two functions here? I get the integral of the sum, which is the sum of the integrals. If I multiply f by a scalar lambda, the scalar comes outside, so I of lambda f has to be equal to lambda of I of f. You combine these things and you show that the linear combinations, right, the linear combinations you do of functions f in the input and can be sent outside of I in this sense. Therefore, I is a linear operator from C to C. Okay, and I claim it's a bounded and therefore continuous linear operator. How do we prove that? Okay, well, it's slightly trickier than the previous time. So in order to prove it's bounded, we want to find a bound for the norm of I of f in terms of the norm of f. So the norm of I of f is the supremum of these guys. So let's try to find a bound for I of f of t. And that, of course, is just this thing here. And we're going to bound this by something that depends only on the infinity norm of f. Okay, here's something about Riemann integrals that we know from calculus, right? The integral of a function over an interval is at most the length of this interval times the maximum, the largest, well, the sup of the function inside. Right, so everything with absolute values. Now, I want to get a bound here. Eventually, I want to bound the supremum here of I of f of t over all t, right? Because that's the sup norm of I of f. Therefore, I'd better get rid of t here. But that's easy. Because t is between a and b, right? So this distance is at most b minus a. Here I have the supremum of f in the interval from a to t. If I enlarge that interval to the larger interval a to b, this can only get larger, right? Computing the supremum for a larger set. But what's the supremum over all s between a and b? Well, that's the sup norm of f. Okay, so this last thing doesn't really depend on t, and therefore I can put a sup here. When I put a sup here, I get that the infinity norm of f is less than b minus a norm of f for all f. Therefore, the ratio of the norm of I of f to the norm of f is at most b minus a. And this linear transformation is bounded. Again, it turns out that this bound is sharp, meaning it's actually attained. So what I've done so far shows that the ratio is bounded by b minus a. You can check that for the function f constant equal to 1, this is achieved. So the sup is exactly equal to b minus a. Right? Good. One last example before we go. Now we're going to look at something that's linear and discontinuous. I'm going to change my setup only slightly by looking at a smaller family of functions, or I'm not going to look at something defined over all continuous functions. I'm going to look at a subspace of this set. Right, so the subspace we're going to consider is the space of continuous functions over this set, such that there exists a derivative of f. Let's move back to 0, 1 here, just because it's slightly more convenient. Look at all continuous functions that are differentiable at a half, right? A half could be any number between 0 and 1. I picked a half because I like a half. There's no particular reason. Okay, this is not the space C. It's a subspace of C in the following sense. It's a subset of C that contains a 0 element, and it's closed by linear combination. So if I take two functions that are differentiable at a half, they're continuous, their sum is also continuous and differentiable at a half. And the same if I multiply it by a scalar. Over this space, I can define this, called L, this linear function. Right, so linear function means it's a linear transformation to R, right? So the counter domain is R. And the transformation takes f and maps to f1 half, f1 half. This is linear because, again, if I add functions, the derivative of the sum is the sum of derivatives, and I multiply by a scalar, multiply the derivative by that scalar, it's linear. But this is not continuous. And this is not really kind of an extraordinary fact, but it's important that you learn why this is the case. First, I'm going to draw a picture, and then I'm going to give a kind of explicit example that describes what I'm showing. So, okay, why is this not continuous? Suppose I have a sequence of functions in D, and this function converges to 0 in the infinity norm. So the norms of the functions go to 0. So what does this tell me? It tells me that, there is a very narrow strip. Let's say this is epsilon, epsilon. So the 0 function has a graph over here. Sorry, I'm only talking about 0, 1, right? So it should be here. And this is 1, this is 0, this is a half. So let's pretend for a moment that L is continuous, right? So that means that given that f sub n goes to 0, it should be that L of f sub n, that is the derivative of f sub n at a half, goes to the derivative of the 0 function at a half, which is 0, right? But that clearly doesn't need to be the case. And why is that? Because, okay, I have a narrow strip, and I know that my function f sub n, its graph must be in this narrow strip, right? So if, say I take n such that norm of f sub n is less than epsilon, I know that this holds for all large enough n. Right, so I have this narrow strip, and my function has values in here. But still, it can oscillate very much. It can, even though it has very little space to go up and down, if it goes up and down very fast, it can be that the derivative here is very large, maybe even arbitrarily large. maybe it's even true that when the larger n gets, the narrower the strip gets, but at the same time, the derivative is getting larger. And I'm going to show that that's possible by giving you a specific example. It's a function that's designed to oscillate a lot, but at the same time it shrinks. So, okay, what's the... And I'm just going to throw the example at you, and then we're going to see why it works, right? So I'm going to build a family of functions that belongs to this space, converges to 0 in the infinity norm, the sup norm. At the same time, the derivatives do not converge to 0. Okay, f sub n of t is by definition 1 over n sine of n squared t minus a half. And this for t in 0, 1. Okay, and the good thing about this example, sine has oscillations, right? The oscillations are getting larger because of this guy. Okay, let me make this more precise. What's the norm of f sub n? Well, actually, I don't need to know what it is. I just need an upper bound. And because the sine is upper bounded by 1, always, no matter what I have inside, the norm of f sub n, the sup of this, is bounded by 1 over n. So this goes to 0. And I'm in the standard situation, so I know that the norm of f sub n goes to 0. Therefore, f sub n goes to 0 in the sup norm. But what's the derivative? What's the linear functional computed at f sub n? Well, that's just the derivative of f sub n at a point a half. And I can do that by the chain rule, right? When I differentiate the sine, I get the cosine. I get this factor of n squared that comes outside, hits the n, this becomes n. And then I get the derivative of the sine, which is a cosine. Well, at n squared t minus a half, t is equal to a half, so that's 0. Cosine of 0 is 1. So this is the derivative. This is it. And this goes to infinity. So this is precisely like the drawing I had before. These functions are getting closer and closer to 0 in the sense that they lie on a narrower and narrower strip, but that they oscillate so much that the derivative is going to infinity. So that's one example of linear function that's not continuous. And it's important in many ways. It's a very basic example that illustrates the following fact. We talked about integration before, and integration was a continuous linear operation. So it's a good thing. We can do analysis with it very easily. Differentiation, on the other hand, it's not continuous, at least with respect to this norm, right? So that there's no way that by controlling the sup norm, we can control derivatives. And that sometimes causes problems. For instance, if we want to prove existence and uniqueness for ODEs, more or less the first thing that we do is to turn that into a problem about integrals, not about derivatives. And the reason is that integrals behave a lot better than derivatives. And this is a kind of a very basic and very fundamental manifestation of that phenomenon. Okay, so that's it for linear functionals, linear operators, or linear transformations. Multilinear transformations are going to be in the next video. You're going to see convolutions, matrix products, and a few other things. Thank you.